Welcome to this lecture on an introduction to trees. In this lecture, we're going to look at some motivations and applications of trees. We're going to talk about some of the key properties and terms that we'll use when describing trees, and then we'll look at different types of tree traversal. So why do we need trees as a data structure? Well, they're very useful in representing hierarchical data. And here are some examples where this might appear. You can think of on your computer, you have a file system that contains directories, which contain other directories, which contain files, and so on. And these are nested directories, and these form a hierarchy that starts at the root of your file system and descends down towards the files. Okay. A family tree is, of course, well represented by a tree. Parents have children, which have more children, which have more children, and so on. Okay. If you think about when you write a program and it gets compiled, uh, the first part of the compilation process is when the compiler forms what's known as a parse tree. And a parse tree is something that says, let's take the string that is the contents of the program, which is just a sequence of characters, and let's break it up into the bits, the parts that are logically dependent upon one another. So if you have an if statement which says if this condition, then this happens, else this other thing happens, that is part of a parse tree where there's an if and an else condition, and if the if is true and if the if is false, you go in different directions. And function calls, this function might call this function and this other function and this other function. So there are parse trees within programs when you compile your program. If you're playing a turn-based game like chess or checkers or Go, you can think about the possible moves. So you can think about, if this is the board for the beginning of the game of chess, you have all your pieces lined up in the rows on the two sides, and the first player makes their move, and they have a number of moves that they can make, which lead to different board states down here. And then the second player can make their move, right, from each of these states, and you can imagine a game tree of all possible moves for the game of chess or whatever else if it's a turn-based game. Okay, so let's go over some important terms. You're probably already familiar with the term vertex or node. Here in this example right here, all of the letters in the ellipses, these are nodes or vertices, okay? And the edges in a tree connect pairs of nodes together. So H has an edge to B, H also has an edge to D, and so on. A path in a tree is a sequence of nodes that are connected by edges. So HDC is a path, but so is FBC and THDC and so on. Okay. Now the root is a special node in the tree, and oftentimes we draw it at the top of the tree if we were to draw the tree. But a root is nothing more than a specially designated node. So really, the fact that you might think that H is the root is not really necessarily true here, just because we drew it at the top. I mean, T could be the root, right? If I dragged T all the way up here and said, well, T is connected to H, which has these children, T could be the root, okay? So the root is just a specially designated node, which we usually draw at the top of our diagrams, and the descendants go from there. And if you have a root, not all trees have to have roots. You can think about a tree that doesn't have to have a root. If you use a tree to represent, say, a molecule or some other natural structure, right? It doesn't have to have a specially designated node, but if it does have a specially designated root, then you can define all these concepts. A subtree is a portion of the tree that is that starts at a node and goes away from the root. So if H is the root here, then the subtree rooted at D is what I've circled here, okay? Or the subtree rooted at T is what I've circled here. Right? A subtree could just be a node by itself. The parent of a node, of course, is the node. If you think about paths as going from the root to some other node, like H goes to F, the parent of F is D if H is the root, okay? But if If some other node was the root, then the parent-child relationship could change. Of course, child, again, is in relation to the root. So if H is the root, then F is the child of D, okay? Sibling nodes are nodes which have the same parent. So again, if H is the root, then B, D, and T are siblings, and C and F are siblings, and H has no sibling. We know that a leaf node, if there's a root, a leaf node is a node which has no children, and an internal node is a node that has children. Okay, so B, C, F, and T are all leaf nodes here, and D and H are internal nodes. And we can generalize the idea of parent and child as ancestor, which is a parent or like a grandparent, or anything higher than that, or child could be generalized to descendants. So all of the nodes below H are descendants of H, if H is the root, for example. And H is the ancestor of every node in this tree, if it's the root. Okay, we can talk about some properties of trees. So if we're thinking about a path, the length of that path is the number of edges crossed. So if we talk about the path from B to C, we go from B to H to D to C, and that crosses 1, 2, 3 edges. So the length of that path is 3. We can also think about the depth of a node X is the path length from the root to X. So the depth of B is 1, because from the root H, we go down 1 edge. The depth of T is also 1. The depth of D is also 1, but the depth of F is 2, because we have to cross 2 edges to get there. And of course, if the depth of B, D, and T are 1, the depth of H is of course 0. Okay, so the depth of the root is 0. We can also talk about the height of a node. The height of a node is the length of the longest path from that node to any descendant leaf. So the height of T is 0, because it has no descendant leaves. The height of B is also 0, but the height of D is 1, because it has 2 descendant leaves, each with distance 1. Okay, we would take the maximum of those, but they happen to be the same. The height of H, of course, which is the height of the entire tree, is 2, because there are 2 such paths of length 2. Okay, so the height is the length from a node to the deepest leaf. And of course, a tree can never have a cycle. If it does, it's not a tree. And because of this property that it can never have a cycle is a loop where, H goes to D, D goes to F, and F goes back to H. That would be a cycle, right? But a tree cannot have such a thing. Because it can't have a cycle, and because a tree has to be connected, a tree with n nodes always has n minus 1 edges. So you notice there are 6 nodes here, and there are 5 edges. And that's true of any tree. And you can prove that, if you think about it, you can prove it inductively. And there's also always only one simple path. A simple path means not repeating any nodes or edges. There's only one simple path between any pair of nodes in a tree. So if I think about going from B to T, there's exactly one simple path to get there. Because if I tried to go a different way, if I tried to go down here, then I have to come back, and that would no longer be a simple path, because I'd be repeating this edge and H. Okay, so these are some properties of trees, of all trees. Now, the last thing I want to talk about today is traversal of trees. And there are 4 different types of traversals that I want to discuss. And we're going to discuss these 3 primary traversal mechanisms or methods from the perspective of a node X. What is an X? Well, X could be any node. But if you think about from a particular node's perspective, what do we do in order to do these different traversals? And the different traversals are called pre-order, post-order, and in-order. And these may sound familiar because we have already talked about infix, postfix, and prefix notation for mathematics. And these are analogous orders. So let's talk about pre-order first. In pre-order, we're going to visit X and then visit X's children, okay? And so this means that if we're talking about if this is node X, X could be any of these nodes, but if we're thinking about a particular node X, we're going to visit that node first and then all of its children, okay? And then if we think about, well, if this is X, we're going to visit X first and then all of its children, okay? and so on. So if we do pre-order traversal, we're going to end up with H, then perhaps B, then D, then C, F, and T. And that's what I've written here, H, B, D, C, F, T. But that's not unique, right? We could have done this in a different order. I mean, H has to come first, but after H, I could have gone with D, then F, then C, then T, then B. That's also a valid pre-order traversal, okay? Because the only definition of pre-order is that the node itself comes first, and then all of the children. Now, the sort of opposite of pre-order is post-order, where from the perspective of the node X, we visit X's children first, then X itself. Okay, so we don't visit, if you're thinking about printing all the nodes in this tree, you would not, in post order, you would not print H, you would go to H, and then you would print you would do a post order traversal of all of the nodes and print all the nodes below H, and then you would print H. So if X is H, then we would do everything that is a descendant of H first, and then we would do H. We're doing something here means, say, printing H. So we might end up doing something like we would print B, then we would go to C, and then F, and then D, and then T, and then H. And I think that's what I've written here, B, C, F, D, T, H. Yes, that's what I've written there. But again, that's not the only post-order traversal I could have come up with. In other words, I could have done, I could have done F, then C, D, then T, then B, then H. Okay, so this is not a unique order for post order either. But what is important here is that the children go first and then the node. Okay, the third major type of tree traversal is called in order. And in this order, we visit the children that are lesser than X, then we visit X itself, then we visit the children that are greater than X. So this only works for ordered trees. Notice that pre-order and post-order work for any trees, but in order, you have to define what lesser and greater are in order to have a valid in-order traversal. So here, of course, this would be B, then C, then D, then F, then H, then T, which is what I've written here. Okay, and that is unique because we have a definition of, B is less than C, C is less than D, D is less than F, which is less than H, which is less than T, right? So again, just to reiterate, we would go, if this is X, we would do everything less than X, then everything greater than X, okay? And we would recursively do that for every single node. So when we got to D, for example, we would do everything less than D, then everything greater than D, okay? All right, the last type of traversal that I want to mention, which is not one of these, it's not as similar to these three, it's called level order traversal, okay? And we visit the nodes by increasing depth, okay? So that means we visit H, then we visit B, D, and T, and then C and F. So we visit everything on the same level in that order, okay? So that's what I've written here, H, B, D, T, C, F. This is analogous to breadth first search. And in order to implement this, we usually use a queue. And the way that queue would work is we would put H on the queue, and then we would pop H off the queue and put on all of its children, B, D, and T, right? And then we'd visit B and pop it off the queue. And then we'd put on all of its children, but it has no children. And so then we'd visit D and put on all of its children, which are C and F. Whoops, no, we're not visiting them yet. So we'll put C and F on the queue, and then we'll visit T, and then C, and then F, and then we're done, okay? So this is like breadth first search on a tree. It's level order traversal. So that's the introduction to trees, and we'll keep talking more about how to use, represent, search, etc. trees as we go forward.